Sim, who is still a postdoc at UCLA, but he's going to move to the UK in January. And the expanded subtitle is How to Distinguish Hazing and Confinement in examples using symmetry protected topological phases, or SPTs. And the beautiful thing is that all the earlier speakers of the day were wonderfully arranged to set this up for me. Yeah.
Fantastic. Thank you.
I was like, how can you possibly have such this? Okay. So phases of gauge theory are important in all walks of life. I don't need to convince you of that. Let me just mention two different walks of life briefly. There's particle physics, which is an SU3 times SU2 times U1 gauge theory. And that alone already realizes two interesting phases of gauge theory. The SU3 color gauge group is QCD is confined, and the electroweak gauge group is Higgs. So everything is already contained in there. And earlier today, we heard in a lot of detail about the Higgs phase of U1 gauge theory or Z2 gauge theory in the context of superconductors. So, for example, a PCS superconductor is something that, at least in its original simplest incarnation, Higgs is U1 to Z2. And here I'm throwing around the word phase lightly, and the main point of the talk, of course, will be that one has to be careful what one means by it. Things are a confining phase in these theories because, at least in the standard model, there are fundamental matter fields. So one should really, I didn't write the word phase on the board yet. If I had, it should be in quotes. And as I said, a lot of the setup that I need was already reviewed by Maria and by Ruben and by other speakers, but I'll mention some things again briefly. So the both old and modern way to characterize gauge theory phases is to look at loop operators. Use loop operators as order parameters for different phases, and the values of large loops tell you what kind of phase you're in. This was understood in the early days of the subject. And the modern incarnation of this statement is that these loop operators are charged under various notions of higher symmetry. In this case, this would be a one-form symmetry that acts on the loops. And whether or not these various one-form symmetries are broken or unbroken tells you what phase you're in. All right? Very good. Now, the crucial point is that the existence of one-form symmetries, electric or magnetic, is predicated on the absence of certain in principle allowed matter representations. So let me give you two examples. Let me repeat ones from this morning's talk. So Ruben discussed U1 gauge theory with a magnetic one-form symmetry, and this magnetic one-form symmetry was there because there were no magnetic monopoles. Later he added them, but in the beginning he didn't have them. So that's one classic example. And we could easily make not a billion examples as well. So for example, we could consider pure SU2 gauge theory. I'll just write this example here. SU2 gauge theory, but with matter not in the fundamental representation of the example atomic matter. Also a fun subject. And this has a Z2 electric one-form symmetry that protects the under which the fundamental Wilson line is charged. And if this symmetry is unbroken, you're in a confining phase. And if it's broken, you're in a deconfined phase. So for example, this is the way you detect the deconfinement phase transition as finite temperature classic theories. Very good. Now, I would like to discuss, I'd like to find the next blackboard. to discuss QCD-like theories. So theories, non-Wheeling gauge theories, that have fundamental matter. Okay. So the canonical example for particle physicists is QCD. This is an SU3 gauge theory with quarks, Dirac quarks, in the 3 of SU3, and then there might be very good, right? One or several of those. So these are in the fundamental of SU3. Very good. So as we heard from Maria, this theory does not have a one-form symmetry. And indeed, this is a small n theory. And indeed, if, for example, other simulations show you that if you keep this theory up and study it at finite temperature, you do not find a sharp phase transition between the confining low temperature regime and the high temperature regime, where morally speaking the theory is deconfined, but not sharply so. So at least as a function of temperature, the phase diagram in QCD is smooth. Now, incidentally, these simulations at finite temperature are possible because finite temperature QCD doesn't have a sign problem from that. That will not be the case for the theory that I'll discuss in a second. Now, a closely related fact, closely related to this, that these theories do not have a one-form symmetry, that they don't have a sharp finite temperature phase transition, is that in theories with fundamentals, there is also no sharp distinction between Higgs and confinement. Okay, so a related fact. A piece of lore is that there is no sharp Higgs confinement distinction or criteria. Because any such distinction in other examples that we know of would make use of a one-form symmetry. And that, plus a lot of examples and experience, suggests the idea that just like in the case of the finite temperature transition, these two regimes, I'm not going to call them phases anymore if I can help myself, are smoothly connected. So that, at least in some cases, you can continuously interpolate between the Higgs and the confinement phase. If you use fundamental Higgs fields, enough of them at least, you can clearly Higgs the gauge group down to nothing, so you can produce a gap in trivial phase, and this is what also happens in the confining phase. If you're lucky, you can interpolate between them. Now, the sort of rigorous cornerstone of the subject is the theorem of Franken-Schenker, and also related developed by Banks and Rabinovich, that showed that at least in certain lattice models, certain fairly special lattice models that we heard about this morning, these two regimes are indeed rigorously connected without a phase transition. And since then, this has been observed in tons of examples with and without supersymmetry. It turns out that Higgs confinement continuity is particularly nice in these theories with supersymmetry, where a lot of examples were accumulated. And so this has become an element of standard law that these two things should not be distinguishable. And one of the things I would like to do in this talk, and depending on how much time I have, might be the only thing I'll do in this talk, is to give you a simple example where this breaks. And for reasons of brevity and pedagogy, I've decided to omit the more complicated examples, more complicated SU3 QCD examples that actually have some interesting applications to, hopefully, the real world. It's not something I get to say all that often. Let me, in this context, mention two related strands of recent work, which are very inspiring. One is the work of Alexa and collaborators, who suggested that if you study QCD at finite density, which is sufficiently high density, is in a Higgs phase, you may actually be able to differentiate between Higgsing and confinement using properties of superfluid vortices. High density QCD is in the superfluid phase, and they had a bunch of interesting ideas along these lines. And a second strand that we heard about from Ruben this morning is the idea that one might be able to characterize Higgs phases as SPTs. Now, the SPTs that we heard about involved one-form symmetries, importantly, either fundamental or emergent. These theories will not have one-form symmetries, so correspondingly, I'm not going to be talking about the same type of SPTs, but nevertheless, SPTs of some kind will make an important appearance. And so the reason Higgs confinement continuity breaks in the examples that we study in our paper is because of SPTs. So since SPTs have been mentioned so often, I'm not going to say a lot about them, and that's good because I don't have a lot of time. But let me just say a few words, just to remind you. So an SPT is a topological action for background fields, at least in the high energy parlance. And it's not just any topological action for background fields, it needs to be, for whatever reason, suitably rigid with a quantized coefficient. And its defining feature is that if you study the system in the presence of a boundary, then there's a Mauli inflow from the bulk on that boundary, so that there's necessarily something non-trivial living there. And so you can characterize an SPT either by this topological inflow action in the bulk or by the anomalous boundary. So I'm going to take the bulk point of view here, and I'm going to say nothing about boundaries. The most famous example, and perhaps the simplest, is a Chern-Simons term, let's say in 3 dimensions. So imagine we have a gapped theory in 3 dimensions that also has an unbroken U1 symmetry. For SPTs, as we heard many times, it's very important that the symmetries that you're talking about are not spontaneously broken, otherwise they can trivialize the SPT. And you can have a completely gapped theory with an unbroken U1 symmetry that at long distances flows to something like this, where this is a background field for the U1 symmetry, it's not dynamic. So the theories are completely trivial as far as dynamics are concerned. Now, the magic is that large U1 gauge transformations quantize this coefficient. And then if for whatever reason you find yourself in a situation that as you dial parameters, you find one value of k in one regime and a different value of k in another regime, those 2 regimes have to necessarily be separated by a phase transition. Now the vanilla situation for SPTs is that the theories are gapped, but in fact many authors recently have considered gapless SPTs, so if you're sufficiently careful, you have to be quite careful, you can also study such things in the presence of gapless degrees of freedom. As I said, for example, the QCD example is a superfluid, so it has a Goldstone boson. So
what does that mean if it's gapped? Does it mean that the degrees of freedom coupling to the symmetry are gapped? But
it means that there are no dynamic fields in the low energy effective theory. The low energy effective theory only has background fields.
But you said there are gapless.
I'm saying if you add gapless degrees of freedom, you have to worry that those gapless degrees of freedom might eat the SPT, roughly speaking, by doing a field redefinition. But this doesn't always happen, and you can study when it happens and when it doesn't. So you're not forbidden from ever talking about this, and it's interesting to do stuff. Good, so this is an example in 2 + 1 dimensions. I would like to discuss QCD in 3 + 1 dimensions. There are no Chern-Simons term there, and at least from the perspective of a high energy physicist, the next most simple SPT that shows up is theta terms. So for example, you can write a theta term for U1 symmetry, a U1 flavor symmetry. I guess I call this A here. And the theta term that I'll be interested in is actually a theta term for gravitational background fields. So the thing that's suitably normalized integrates to the signature of a Euclidean form manifold. Now, the way that I've normalized these terms least on spin manifolds, implies that the theta angles have their standard 2 pi periodicity. And of course, the theta angles are continuous parameters. And I emphasize the fact that the rigidity of SPTs relies crucially on some kind of quantization. But famously, if you insist on an orientation reversing symmetry, so either parity or time reversal, or any other mixture of any other symmetry that you can imagine that reverses the orientation, then these things are frozen to be either 0 or pi. 0 being, in this case, the trivial SPT, and pi being the non-trivial. And then you see that these SPT actions only lead, at most, to a sign in the partition function if you turn on D1 backgrounds or non-suitable manifolds. This thing becomes much more interesting and much more complicated if you go away from spin manifolds. For example, you go non-orientable manifolds that get a much more fine-grained quantization of the coefficient and of SPTs, which many of you are experts in. This very simple notion of SPT theta angle is sufficient for the examples that I'll discuss today. But using the more fine-grained SPTs, you can prove discontinuity results about theories for which this simple theta angle criteria will fail. All right. So what's the simplest example of an SPT with gravitational theta angle equals pi? Well, you can take a biofermion. I guess I need to move this up. So a two-component fermion in 3+1 dimensions, which has the following action. And then there's a mass term, which in particle physics is sometimes called the Majorana mass, which is generally complex. But if you insist on time reversal, parity, CP if you want, then time reversal complex conjugates M. So if you insist on time reversal symmetry, you will have real M. And then you can discuss the phase diagram of this extremely simple free theory as a function of M. Now, it's possible to regularize the theory in such a way, or in other words, choose counter terms in such a way that when M is bigger than 0, you get the trivial SPT. This is a result that's kind of entwined with the Balmer-Whitney theorem. And if you instead take M to be negative, then using many different arguments, for example, the mixed anomaly between the U1 axial symmetry rotating fermion and gravity, you can convince yourself that you instead have gravitational theta angle equals pi. So the gravitational theta angle counts negative mass Majoranas mod 2. More precisely, what it does unambiguously is detect whether or not Majorana has flip sign. And now I told you before that if the SPT jumps, then you necessarily have a phase transition in between. And here the phase transition is obvious because it occurs at the point n equals 0 where you have a massless fermion. In the positive M phase, here you have the complex M plane. In the positive M phase, you have a gap theory with the trivial SPT. In the negative M phase, you have a gap theory with a non-trivial SPT. And at n equals 0, you have the SPT enforced phase transition. In this case, it's second order. Of course, in general, that doesn't need to be true. Now, if you give up on time reversal, if you break time reversal explicitly, these SPTs stop being protected. And indeed, you can continuously interpolate in this phase or that phase while remaining in the gap region without encountering the massless point. And that of course goes a long way to explaining why these phases are physically essentially identical. And nevertheless, in this situation, you're forced to drive through the phase field.
Is it true that the gravitational theta angle is always a diagnostic for time reversal protecting this field?
Well, without time reversal, nothing pins theta d to these two values.
My question was more, are there other symmetries other than time reversal?
So as long as we're discussing only spin manifolds, and without all the associated subtleties of going beyond that, you need an orientation reversing symmetry. T, CT, P, CP, but something that something that flips the sign of R with R. If you only have an internal symmetry, then it will not be. Yeah.
It's T squared.
Minus 1 or the F.
Minus
But in all the examples I'll discuss, I'll actually have both. No, sorry, that'll be true in all the examples. All right, so let's proceed to my example. So what I'm going to do is to take this simplest possible example of an SPT and soup it up in the context of gauge theory. So that the SPT and force dump associated with the free fermions in mass actually happens in the context of a gauge theory transition. So, as I said, I don't have time to discuss QCD. I have barely enough time to discuss the example I'll talk about. So I decided to choose one of the classic examples of Higgs confinement continuity, which is in the old paper by Saskian and Dimopoulos and Raby. So this is an SU2 gauge theory with what you might call one flavor, or one Dirac flavor in the fundamental. But because SU2 is pseudo-real, you can repackage that into two Weil fermions that are fundamentals. So here, this is an SU2 flavor index, and A is an SU2 fundamental color index. Alpha is a spinor index, which I guess I can sort of omit right here. So this is a one Dirac fermion in the fundamental of SU2 repackaged as a doublet of Weil fermion. Very good. And I'm also going to add a quark mass. And the quark mass actually preserves the full gauge and flavor symmetry. If you're careful about quotients, the total symmetry is actually SO4, gauge and flavor. Very good. So we're going to take this to be positive, so that by Lafayette we will get a trivial SPT in this theory without further modifications. Very good. So now let's add to this theory a Higgs field. We want to drive the theory to a fully Higgs phase, and so we must add a Higgs field in the fundamental representation of SU2. And I don't need to do this, but it will be nice for me to also preserve the SU2 flavor symmetry, and I can do it. So I'm going to add essentially what looks like a standard model Higgs field. We usually think of the Higgs field in the standard model as being a doublet of the SU2 weak gauge group, but in fact there's also an SU2 custodial symmetry that acts on it. So you can think of it as a vector of SO4. This is a real SO4 vector. Very good. All right. I apologize. I still haven't figured out the correct word to use these towards them. I suspect I will not.
There is no such thing.
It's yeah. All right. So let me review one or two elements or observations from the Saskian and Friends paper about why you might think that Higgs and confinement are continuously connected here. Let me first say a few words about the confined phase. In the confined phase, you expect to get color neutral bound state. So, for example, you could get a bound state of the Higgs field and one of the fermions. This is color neutral. And if you decompose into the SU2 flavor symmetry, you get a singlet plus a triplet. Now let's look at the Higgs phase. And it turns out that the Higgs phase of this model automatically, if you wish, has the following beautiful color flavor one form. You can engineer that by choosing a suitable SO4 invariant potential. So let's choose the following Higgs vector that identifies color and flavor indices. C here is real. In fact, I can choose positive. So this is the color flavor locked form of Higgsing in this theory. And what does it do? It spontaneously breaks this symmetry down to its diagonal subgroup. I'll call SU2F prime. So SU2 color is completely Higgs. This web is not invariant under any SU2 color rotation. The theory is gapped. But it is possible to maintain an SU2 flavor symmetry by mixing with the broken gauge symmetry. And under this color flavor identified set of indices, the original fermions of the model go to something like this, right, which also decomposes into a singlet plus a triplet, now of the unbroken SU2F prime symmetry. So both phases have similar particles transforming in similar representations, identical representations of the unbroken symmetry. Yes?
What are the Yukawa couplings look like?
So far, there are no Yukawa couplings. This is crucial. And in fact, in this model, you can easily see that there are no normalizable Yukawa couplings. So Susskind and friends considered this model without Yukawa couplings.
There's no F3U1 symmetry for the F1 on the
There's this, the U1 is the global or gauge. Well, that's the carton of the SU2 flavor symmetry, if you wish. You can think of my Higgs as a complex Higgs if you only focus on the U1 of the flavor symmetry. I've just exhibited the full SU2 symmetry. But this theory doesn't have any Yukawas, and it doesn't have any normalizable Yukawas, so it won't generate them. So I think it's fair to say that you can study the theory without them, as Susskind and friends did.
Doesn't it have two flavor symmetries now?
That's one
Fermion separately and Higgs field separately.
Ah, good. Maybe that was the point of your question. Yeah, right, indeed. In the absence of Yukawa couplings, there are two separate flavor symmetries. I preemptively identified them. Yeah. If you don't identify them, then this trick won't work. Because then this fermion will transform one index under one SU2 and one index under the SU2 of the Higgs. So in order to get a nice matching between the confined and the atomic phase, you can identify them. You don't have to. But you're completely right that I will very shortly add Yukawa couplings, and then they become inevitably linked. So basically what these people said is, look, all these things match very nicely, and also there's a theorem by Fratton and Schenker that says that these two phases should be continuously connected, so they're probably continuously connected. This is the kind of, the origin of Higgs confinement continuity. Very good. So I would like to violate this continuity by somehow engineering in an SPT enforced transition in between the confining and the Higgs regimes. And the way I'm going to do it is by adding Yukawa couplings. Okay, so if you want to preserve the gauge and the global symmetries, then the Yukawa couplings you can add look like that. They're dimension 5 operators. Right. The fermions transform like this. principle, there are two Yukawa couplings you can add. One that involves one contraction of gauge and flame, and one which involves the opposite one. If you're a quantum physicist, this might remind you a little bit of the dimension 5 Weinberg operators of the Standard Model. Now, I'm going to insist on preserving all my symmetries, including time reversal. So time reversal will require those Yukawas to be real. That's the thing we don't expect you to in this time. And for simplicity, I'm going to take them to be positive. You can also consider other choices. Very good. Now, these Yukawa matrices don't do anything if we are deep in the unhiggsed phase, right? If we give the Higgs field a large positive mass squared, so we're very far from, safely far from the Higgs regime, then these terms don't contribute to the fermion mass matrix. And in fact, if we take the Higgs max asymptotically large, then we make contact with QCD without the Higgs and the Yukawas, in which case we set things up in such a way that we get the trivial SPT. Theta equals 0. Now, let's quickly study what happens when you turn on a VEV for the Higgs field. So plug this VEV into here, make the VEV very large, so you're deep in the weakly coupled Higgs regime, right? I'm not going to do anything at strong contact. And then let's analyze the fermion mass matrix. Now, I already told you that the fermion decomposes into a singlet and a triplet, the unbroken flavor symmetry. And you can check, one or two line calculation, that the mass of the singlet in the Higgs phase is m minus y2 d, and triplet. Sorry, I might have switched them actually. Turn that around. The singlet is the trace of the fermion. The triplet is traceless, and because the triplet is traceless, it doesn't receive contributions from Y1. So you see that for the positive Yukawas, which is what I chose, the singlet stays put, but the triplet crosses the mass threshold and gets a negative mass. Because the triplet has 3 Majoranas in it, that means that we get the gravitational theta angle 3 pi, sorry, which is equivalent to pi about 2 pi. So a non-trivial SPT in the Higgs phase. So, by the general SPT logic, this Higgs confinement transition in the presence of the Yukawas is necessarily not smooth. There must be at least one phase transition separating these regimes as we dial the Higgs graph. So this is the basic slogan of our paper and of the talk. Yukawas allow you to destroy Higgs confinement continuity, in part because they destroy the Vafa-Witten theorem. Any questions?
So in part what? I didn't catch the last what you said.
In part because they destroy the Vafa-Witten theorem. The Vafa-Witten theorem ceases to hold in the presence of certain types of Yukawa continuities.
Which Vafa-Witten theorem?
Sorry?
Which Vafa-Witten theorem?
Well, the one that tells you that, roughly speaking, the partition function is positive. The measure is positive. Yeah. Very good. Now, this was my SU2 example, which is the only thing I have time to run through in any detail. And I could either stop here for questions, or I could say in words for a few minutes what the main features of the QCD example are.
On the other hand, the argument that the spectrum is described by the same gauge invariant operator that continues to hold.
That continues to hold. And indeed, now that I'm engineering a transition, I have to actually explain why this matching of the spectrum and the physics in the two phases is not an accidental embarrassment. And I think the way that works is sort of similar to what happens for the free Dirac fermion. Remember that for the free Dirac fermion, time reversal, or for the free Majorana, sorry, the time reversal symmetry really forced you on the slide where you see the phase transition. But if you break time reversal symmetry, you can really smoothly connect these phases. And I think the same is true here. If you allow complex Yukawas and break time reversal symmetries, the SPTs will trivialize, and I think you can probably still smoothly connect the physics that shows that the physics is actually smooth. But if for whatever reason physics tells you that you're stuck on the time reversal preserving slice, then you have to go through the transition. And that's the interesting thing about QCD at finite density. QCD at finite baryon density does preserve time reversal and parity. And so you have a chance of being forced through such a transition.
Do you have to do something to QCD at finite baryon density?
Sorry?
What do you have to do to QCD? Is it automatic?
Which part then preserves it?
That you get these different.
No, it's not automatic. You have to convince yourself that whatever physics takes place in high density QCD generates such a term. But
Yes.
the pairing, the BCS pairing that happens in high density QCD is essentially modeled by what you call it. So that's how you get it.
At high density, how do you get to the confining phase?
So at high density, you're in Higgs phase. The confining phase is.
So you don't have the confining phase.
Well, okay, let me say a few words about the phase diagram of finite density QCD. You have two confined phases. They're different and interesting. So, if you take real QCD and finite baryon density, then here you have U1 baryon breaking superfluid, and we think also a non-trivial SPT. Here at very low densities, you just have QCD in the vacuum, so you clearly have a confined theory, and also U1B is unbroken. Now, the thing that people believe is that there is actually an intermediate phase where you still have a baryon superfluid, but it's kind of a confined nucleonic baryonic, so let me call it baryonic superfluid. So U1B is broken, roughly speaking, because of the nucleon BCS pair, but this is not supposed to be a Higgs phase. And so you see that you have two different confined phases in this diagram. One is the vacuum phase, which is obviously confined. That you can distinguish from the high density phase just by virtue of the fact that the baryon number is broken here. You don't need any fancy SPTs for that. But these two phases both live within the superfluid. And nevertheless, there was this interesting suggestion that perhaps the ultra high density quark regime and the moderate density nucleonic regime are separated by a transition. And even though the symmetry is realized in an identical fashion in both phases. And so we have evidence that the SPT for the gravitational theta angle jumps. So this we can compute pretty reliably. This we have some arguments for.
Is the vertical axis temperature here?
Yeah. So if you heat this thing up, then eventually you will restore U1 baryon symmetry. And people believe that this is the first order transition. And then you can speculate about what this transition looks like, for example. It could also be a first order transition, or it could be second order. Yeah.
Two very good questions. So first off, I guess I'm surprised SPTs is finite temperature. Usually.
No. Everything I was discussing happened here.
So the transition only needs. So you might.
Yeah.
The transition
The only thing that I'm saying is there's a transition here.
Okay. And second question: have you thought about the consequence of measuring space that density is modulating? You have pockets where you're in one phase and
Yeah. So that actually naturally happens in a neutron star.
So again?
That actually naturally happens in a neutron star. Because deep inside the neutron star, you're at higher density, and at the intermediate region, you're at lower density. So you would expect that there's a core that is in this phase, and then a shell which is in this phase. And that means you might have a boundary layer that has the anomalous edge most.
So it's also very cold.
Yeah.
Very hot
So
in normal units, but
I shouldn't have drawn the temperature axis. That was just misleading.
Okay. Awesome.
What are the edge modes?
But if you blindly extrapolate free quark weakly coupled intuition, they'll be some Majoranas at the edge. So this theta equals pi anomaly can be matched by a single Majorana on the three-dimensional edge. But it will be something more complicated.
We have to end here because we are breaking.
All right.
You finished more or less. I mean,
Yeah,
this part you
I understand.
summarized it. Okay. If you have nothing else to say, then well, I'm sure you
Nothing else.
nothing else. urgent to say. And then let's conclude here.